this video, I want to talk about the equations of motion and generically how we might apply them to this condition of general planar motion that we've been working with. So just to kind of rehash a little bit, general planar motion is the motion of an object, or the analysis of the motion of an object or a rigid body, and taking into account the rotation and translation components of that motion. So for example, if we have a rigid body and we have a center of gravity labeled G, we can say that this rigid body is possibly moving or translating with some acceleration of G, and we can also have rotation around that position alpha. Now, the forces or loads that are causing this can be varied, right? We can have forces, let's call them F1 and F2 and maybe F3. We can have moments, so I can apply a moment here, for example. I can apply a moment here, for example. And we can have any possible combination of those things. So now we have loads which are causing rigid body rotation and possibly the translation as well. So if we want to apply the equations of motion, we should be relatively familiar with what those look like at this point. So we can sum the forces in the x and say that the summation of those forces causes some acceleration of that center of gravity G in the x direction. We can sum the forces in the y direction and say the same thing now in the y direction, and we can sum the moments. Noting here that I've used the moment of inertia with respect to that center of gravity G, and I'm summing the moments therefore around G as well. So all of this, so far is written with respect to the center of gravity location G that I've labeled, and I'm kind of writing everything as it relates to that point. However, it may be convenient to, in some cases, apply these equations to some point other than the center of gravity, perhaps a location where several of our forces are applied, or something else that we particularly care about how it's moving. So if we apply our equations of motion to a point that is not coincident with G, we can write effectively the same equations for the summation of forces in that nothing really changes from a force perspective. We're still interested in how the rigid body is translating, so its accelerations are still with relation to G, purely because we approximate the whole rigid body, or kind of take the whole rigid body and equate it to a point located at G for that purpose. However, it may be convenient to sum the moments about some other point, which I'm going to label A. I can arbitrarily pick a location up here, A, for discussion. And if we do that, we can rewrite these equations by taking into account the motion around G, but now including a term which accounts for the fact that the position of point A is itself moving with respect to G. So we have to include this term, which is the inertia, basically, or an inertial term related to point A, and d here represents the distance between G and A. So we can measure that distance and use it in this equation. So now that we've kind of established how we might apply these equations to, say, some other arbitrary point, where this really kind of becomes useful is if we know where the instantaneous center location is. So if I apply this same principle to that instantaneous center, the nice thing about doing that, and if we know where that point is that remember that the instantaneous center represents the point at which the rigid body is in pure rotation around the instantaneous center, and therefore the instantaneous center is not translating at that instant in time. And therefore, our first two equations, our summation of forces equations in this case, drop off, and instead we focus on the summation of moments around the instantaneous center, our moment of inertia about the instantaneous center, and our angular acceleration. So in this expression, we need to note that our moment of inertia about our instantaneous center, if expressed in terms of other things that we know, we would write it as the moment of inertia of the body around point G, around the center of gravity, plus the parallel axis theorem term, which is md squared, d being, again, the distance between the center of gravity and the point that I'm talking about, which is the instantaneous center in this context. And what we should see is that if we compare what's going on in this expression with our previous one, basically we're doing the exact same thing. It's just a different way to think about it, because the acceleration is going to be related to the angular acceleration by a equals r alpha, and if we substitute that in up here, we would get the same expression as if we apply the parallel axis theorem to my moment of inertia in this last equation. So it's not really any different mathematically, but it is a different way to think about the problem and a different way to look at the problem that kind of gives us a little bit of simplification. All right, thanks.